The final is 12/12/2012, which is a Wednesday at 4 p.m. and it's going to be in this room, ISB 135. If you have or you are aware of any conflict with that final, I mean same time, final, in the same day, same time, you need to go to the registrar office as soon as possible. They will tell you which instructor or professor gonna give you the makeup. If I'm the professor that's gonna give you a makeup, please let me know as soon as possible so that we find an arrangement and a time to take the makeup exam. If you are registered with the disability services, contact them as soon as possible. I mean today, because the final is gonna be so crowded, so they need you to contact them today. Okay? The final practice exam is already on Moodle. What's included in the final exam? Everything. Chapter 1, Chapter 2, Chapter 3, Chapter 5, Chapter 6, Chapter 7, 8, 9, which we're going to finish today, and a very small part of 10. It's going to be 1 or 2 lectures on Chapter 10. The final info page will be posted. I said here it's posted. I forgot to post it last night. So it's going to be posted online so that you know what I'm going to give you regarding equations, constants. So I'm going to upload it today. As you know, exam 3 grade is online. Thanks for Jake for working so hard to grade your exam yesterday. And the grades are already on OWL. If you don't see your grade there, please contact me as soon as possible, sending your exam ID and the exam ID and your UMass ID. Now, how many of you would like to boost their grade? Raise your hand, raise up your hand. Great, so almost everybody in the class. So what I'm gonna do is I'm gonna open all the OWLs. So I'm gonna extend the OWLs, all the OWLs, so that if you didn't manage to finish any homework, you can finish it whenever you want. It's up to you if you want to. Even if you wasn't practicing, if you were practicing during any exam, if you get it right, the OWL gonna consider it right, and you will be done from some homework that you didn't finish. So I'm gonna open all the OWL homework. There are two good reasons for doing that. First, you're gonna boost your OWL grade. Second, and the most important, that you're practicing while trying to finish what you didn't finish, because everything is included in the exam. So I'm gonna open the OWL. Now regarding the OWL book, so I'm receiving emails, are you grading the OWL book? Are the OWL book mandatory? Yes. So the OWL book, yes, I'm gonna grade the OWL book. The only thing that maybe you're not seeing any grade for the OWL book, because the way that we grade the OWL book is different than the mastery one. So it may tell you, you don't have a grade. But as long as you're doing it and you're hitting the progress button every time you're doing it, at the end I'm gonna get a report of what you did and what you didn't do. Okay? And now when you see the letter O, which is in blue, that means it's optional. It's up to you if you wanna do it or not. You're not gonna be discredited. You're not gonna get extra points for doing that. Yes, please. Chapter 4 definitely on the exam. Did I miss it there? Everything is included in the exam. No exception. Everything. No exception. Nothing is accepted from nothing. Okay, everything. Okay, so with that, we're gonna get started keep going with chapter 9, which probably we're gonna finish it today. And as you know, 3 lectures left. We're gonna take 2 lectures to kind of talk about chapter 10. And if we have enough time, the last lecture gonna be a help session. That means I'm gonna help you with whatever question you send me. Now, the way how to study for the final, if I'm you, I'll just take all the practice exams, all the exams that you took. I would take them and begin solving them. If I feel every time I'm doing Hess's law, I'm doing a mistake, I'm not getting the right answer, I would go to OWL and begin practicing, go back to the OWL mastery section of Hess's law. The same for any other subject matter. I'm gonna be in my office during the final week. If you have any question, if you can't make it to the office hour, just send me an email and take an appointment because it's gonna be a little bit crowded during the final because everybody has a question. So if you can't make it during my office hours, just send me an email saying, "Oh, can I meet with you by that time? For example, for 20 minutes, 1 hour, 2 hours. It doesn't matter. Just send an email so that I keep it track and add you to my schedule." Okay. So with that, we're gonna get started with chapter 9. So on Wednesday, we talked about valence bond theory, in which we talked about how those atoms that we learned about and we learned about electronic configuration, how do they do bonding? And mainly we're targeting covalent bonding because ionic bonding is losing and gaining, so there isn't a real bond there. So we said that, for example, for the hydrogen, which have one S1 as electronic configuration, and another hydrogen which have one S1 also as electronic configuration. Now, in here, I put the electron down just for the sake of comparison, for the sake of the discussion. Definitely, when you're writing electronic configuration, you will just put it up, but it doesn't really matter. So now when I'm describing H2 bond, which is HH bond, what I said that, okay, those two atoms, they're gonna bond, and they only can bond if each one has unpaired electron, at least one unpaired electron. And for the bond to form, the two electrons should be opposite in spin, otherwise they wouldn't be in the same orbital. So the 1s and 1s will combine together to form what we call the sigma bond. And sigma bond. Then we talked about HF, which is an S and a P kind of combined together to give us also a sigma bond. Then we talked about F and F, where P and P combine together, definitely one electron of this P and one electron from the other, with opposite signs of electrons, they combine together to form a sigma bond. And in all of these cases, and all the time, a sigma bond is a single bond. It can't be, for example, the double bond, or it cannot be a triple bond that it is a sigma bond. A sigma bond is a single bond. It can be formed between S and S, S and P, P and P, which is the three cases that we saw in here. In those cases, we can form sigma bonds. Now, definitely those sigma orbitals that are formed, they look different than each other. If it is S with S, it has 0 node. As we saw, you can go back to the slide. It shows no. While S and P, the sigma bonds look a little bit different. And for the PP, it looks also different than the SP when S and P form a sigma bond. Now we get to, the last time we talked about all of these, and we get to nitrogen. So nitrogen is N7 and have 1s2, 2s2, 2p3. So it mainly has 1, 2, 3. And another nitrogen, which I'm just going to represent, it's a 3p. 1, 2, 3. So I have 3 unpaired electrons. In all of the examples that I gave, like H2, F2, HF, each one has only 1 unpaired electron. In this case, each has 3 unpaired electrons. So the first thing, that this unpaired electron and this unpaired electron gonna combine as a PP to form a sigma bond. which is represented in here when a P and a P combine together, they form a sigma bond, which is right there. Here, both of these are the atomic orbitals. That means those of the atom. Those are in the molecule. Then the next one would be this P, this unpaired electron and this P they're gonna combine. But this time, because we already have one sigma bond, they're gonna form a pi bond, what we call pi bond. Then, this one, this last P with this P, they also gonna form what we call a pi bond. And that makes sense because if we look at the Lewis structure of nitrogen, we find it has triple bond. The very first bond is a sigma bond. The second one, this one in here, is a pi bond, and the third one is a pi bond. So, if I'm talking about single bonds, all of them are sigma. If I have a double bond, one of them gonna be sigma, the second one gonna be pi. If I'm talking about the three bonds, one sigma and two pi's are there. Now, what is the difference between a sigma and a pi bond? In a pi bond, the difference is the shape of the orbital itself. As you can see, for the pi, it's kind of formed above and below. This is, not this one, this one. So, for a pi bond to form, it is the P and the P, which look like that. We learned that they look like that. They kind of combine with each other, and they are above and below the molecule. While for sigma, it's in between the two atoms. While a pi, first of all, it is above and below the molecule. Second, it is perpendicular to the atoms. Okay? And this is why pi bonds are weaker or less stronger than a sigma bond. Why? Because they are perpendicular and they are forming like this. While a sigma bond is stronger because it's in the same plane of the atom, it's not perpendicular to it, it's not above it and below. Okay? So, and this is how a pi bond would look like. Definitely the third one would look also as an orbital like this one in here. Okay? So all single bonds are sigma bonds. If I have a double bond, it's going to be formed from one sigma, the same as here. One sigma, one pi. If I have a three sigma bond, if I have a triple bond, one going to be sigma, two pi. So, if you remember when we were talking about Lewis structure, I told you that only carbon, nitrogen, phosphorus, sulfur, oxygen can form double or triple bond. Anything else from the periodic table, they will rarely would do a double bond if ever. And the reason behind that is now more clear for you. Because just imagine I'm talking about a Br, and which is this atom in here. Just imagine, Br is very big molecule, very big atom, sorry, and the other Br is very big. So let's imagine that those are 7 times their size now. So that P and that P is very hard to be formed above them due to the radius of the atom. This is why heavy atoms below carbon, nitrogen, oxygen, sulfur, and phosphorus, they don't do double bond. Iodine can never do a double bond. A Cl, rarely if ever, only if it is in a hypervalent compound, and rarely that would happen. The others, none of the others would form a double bond other than carbon, nitrogen, phosphorus, sulfur, oxygen. This is why when we're drawing the Lewis structure, we don't do a double bond for a chlorine or for an iodine or for a bromine. That doesn't look right. There are some exceptions, but the main ones, no, we don't do that. And the reason behind it is the radius, the big radius of that atom. So if the atom has a big radius, it's not going to be able to form a pi bond, which is a double bond, okay? Now, when we get to CH4, so we want to describe, using the valence bond theory, how methane, which is CH4, forms. So I know that carbon is 6. So it is 1s2, 2s2, 2p2. So I have this. And I know that hydrogen is 1s1. And I'm going to draw the electron count just for the sake of discussion. And it says that I have, for each carbon, I have 4 hydrogens. So I'm going to put the 4 hydrogen around this carbon just to see how we're going to form this 4 bonds. I'm going to put it in here. Now, I'll get started the same as the nitrogen. I'm going to say, okay, this is unpaired. I'm going to pair it with this one, and they're going to form a sigma bond. Then, I want S, usually an S cannot form a pi bond. S and P doesn't form a pi bond, they form a sigma bond. Then I say this with this, another sigma bond, and the unpaired electrons are done. I don't have any unpaired electron. How am I going to form the other? So maybe I only have 2 bonds. How come methane? I'm sure that it exists as CH4. While this theory is just limiting me that, according to the theory, how we deal with the theory, it's just we're going to have 2 sigma bonds. And definitely that was a riddle for a long time for scientists. How come methane has 4 bonds, while according to the valence bond theory, if I put it this way, it doesn't work. It's only going to form 2 bonds. And this comes into the play what we call the hybridization. Okay, what does that mean? From the name hybrid, that means there will be a combination of 2 things and it's going to be in between. That carbon going to have 1 s2 and 1 orbital from the s, because s only here have 1 orbital, and the 3 orbitals from the p. It happens that they kind of combine together and they get to have almost the same energy. And we call this, so that 1s and 1, 2, 3p, they're going to form 4 orbitals, and we're gonna call these sp3, sp3. So each orbital is now not an s, it's not a p, it's an sp3. So what does that mean? Why first I said sp3? It's because 1 from the s, 1 orbital from the s, and 3 orbitals from the p. This is why it is called sp3. Now each one of these, I combine the s with the p. In other words, I'm telling you now the energy of this sp3 equal to that one, equal to that one, equal to that one. This is what I'm saying. And that's the truth, that the 3 sp3, these 4 sp3 now orbitals have the same energy. And now I'm going to take 1, 2, 3, 4, and I'm going to put them according to Hund's rule in this new hybridized orbital. Hybridized orbital. And this now going to explain how in all our Lewis structure we put 4 bonds for carbon, because during all our Lewis structure you put 4 bonds for the carbon, and you expect it to have the carbon to have 4 bonds. And now this is gonna unriddle that, which gonna be 1, 2, 3, 4. According to Hund's rule, if I have 4 orbitals that have exactly the same energy, I'm gonna put the electrons as apart from each other, and they should all have the same spin or parallel spin, which is the case. Now, if I have 4 hydrogens, which have 1 s, each one, and I'm gonna put the sign. This is the first one. This is the first sigma. This is the second sigma. And this is the third sigma. And this is the fourth sigma. And now we can explain how come methane have 4 bonds. Now, all of these, usually the sp anhybridized orbital does not do a pi bond. thing that can do a pi bond is P with P. P with P can do, sorry. P with P can do a double bond. S with sp3 or any of the other hybridized orbitals that we're going to talk about, they do sigma bonds. So this is sigma, sigma, sigma. This sigma bond is consisted of an sp3 and an S, because the hydrogen has an S, 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 S. So if I go back to the molecule, to the methane molecule, in here, when I'm describing it, I'm going to say this bond is an sp3 with an S. Sigma bond. And the same for this one, it's an sp3 with an S sigma bond. This is a sigma bond. Since it's a single bond, it's definitely a sigma bond. It's sp3 with an S. This is sp3 with an S sigma bond. Okay? Now, definitely now your question is, okay, how am I going to know which atoms hybridize? You just taught us that, okay, draw the Lewis structure, this is single and sigma bond. How am I going to know when things go this way, when they don't? So, usually, I'm going to give you a rule that's help you do that without each time going back to all of this, to all what I did in here. I'm going to just give you a main rule for all of this, and that's coming next. Now, usually, this hybridization thing only occurs if in overall, this promotion or this hybridization, we call it promotions of electrons. That means that I'm jumping the electron, I'm making the electrons of the s orbital jump to a p orbital. So we call this the promotion of electrons will occur, or this hybridization might occur if that make the molecule more stable and make it make more bonds. Okay? So that's when it takes place. But even this definition or this kind of guideline is still not kind of very clear. So what we're going to do is we're going to depend on Vesper model to determine the hybridization. Okay? And that's coming next. I'm just going to give you 1 minute because everybody is still writing. Okay. Done? Okay. So, this table tells you for each Vesper model what is the hybridization of the atom that you're determining its geometry. But this table has a little bit of requirements that I need everybody to concentrate, okay, on this part that I'm talking about. So this Vesper one, which is AX2 here, AX3, AX4, AX5, and AX6, it's talking about the electron arrangement. In other words, I'm talking about the electron pair geometry. In other words, if something has AX2E, its electron pair geometry is AX3. If a molecule has AX4E, that means its electron geometry is AX5. If you remember when we were doing that, and we're saying, oh, to know the electron pair geometry, just add 2 plus 1, that's going to add up to the X. 4 plus 1, it's going to add up to there. The same for any other molecule like AX2, E3. I don't know if that even exists, but I'm just going to put it there. So it is AX5. So when I say that the electron arrangement Vesper model, you have to think that, okay, it's, even if you have an E in your model, you have to bring it back to where it comes from. Now, if you have a molecule with a linear shape, AX2 is going to have sp hybridization. And definitely the sp, those sp, that means it have 2 orbitals, because one from the s, one of the p, so it's going to have 2 hybridized orbitals. Hybridized. And it's going to left with 2 p orbitals. So let's do an example so that you can see what I'm talking about in here. So I'm going to start as an example with CO2. So I think everybody now knows that this is the Lewis structure of CO2. The Vesper model of CO2 in this case is AX2. Therefore, it has an sp hybridization. Hybridization. That means when I'm talking, I'm going to just write the CO one more time, but this time bigger, so that we can analyze it. So this bond is a sigma bond because it's a single bond. This bond in each of those bonds up there, come on, is a pi bond. So according to the table, this molecule has two sp orbitals, 1, 2, and it has two p non-hybridized, two unhybridized or non-hybridized orbitals, according to this table. So we know that sigma bonds are formed. In this case, we know that I have this sigma bond is formed from an S, P, and a P. Why? Because this carbon is hybridized to sp. And this bond, since it is a sigma, and usually sp hybridized orbital does not form a pi bond, this is an sp with a p. How did I know that it is a p? Because oxygen valence electrons are in a p orbital. Now the pi bonds are only formed from p bonds. I know that this molecule has two p, so this pi gets formed from p with p from a carbon and p from an oxygen. And this pi bond in here is formed from a p from an oxygen and p from the carbon. So this is how we analyze what kind of hybridization I have and what is this formed of. Pi bonds are only formed from p orbitals because they have to be perpendicular, they have to be above and below the bond. Now, sp or sp2 or sp3, any other hybridization, it's going to end up being a sigma bond. Now, when I say to know how many hybridized orbitals do you have, if you have sp, you count. I have one s, one p, that means I have two hybridized orbitals. Okay, let's go back to the table and take the other example, the second example, which is if I have AX3, that means I have 3 hybridized orbitals. And as you can see, the number of hybridized orbitals kind of coincide or is the same number as the number of terminal atoms. 3, 3. 4, 4 hybridized orbitals. 5, I have 5 hybridized orbitals. 6, I have 6 hybridized orbitals. Now, in case of AX3, it tells you that you have 3 hybridized orbitals, 1 from S and 2 from P, so we call it sp2 hybridization, and I'm going to have 1 P orbital, which is unhybridized. So let's take an example to see so that you can see what I'm talking about here. An example of that would be COCl2. If I figure out the model of this, the Vesper model, it is AX3. That means it is sp, so it must have 3 unhybridized orbitals, 1 from S and 2 from P, so it is sp2. And I have, this is the hybridized, and I'm going to have 1 P, which is non-hybridized. Now, that means this is sp2, this is sp2, and this is sp2. I can only put 3 sp2 because I have 1, 2, 3. This one, since it is a pi bond, it's going to be a p with a p. This one, sp2 with a p. How did I know it is with a p? Because oxygen valence electron are in a p. So this is a sigma bond. This is sp2 with a p sigma bond, because also chlorine valence electron are in a sigma bond, are in a p, and this is a sigma bond. In other words, this molecule has 3 sigma bonds and 1 pi, and it is sp2 hybridized. And we're going to go to the next example. So the next example in the table, it says if it is AX4, it's going to have 4 hybridized orbitals, and it's going to end up being sp3 hybridization. 1 plus 3, that means 4, and it has none of the p orbitals. So would CH4 have a double bond? Would AX4, any model with an AX4 have a double bond? No, because it doesn't have a p. The same for the others. So I'm going to give you an example which we already did for AX4, which is methane, CH4. So again, the Vesper model is AX4. That means the hybridization of this is sp3. Again, the addition of this with that should add up to this number in here, 1, 2, 3, 4. And definitely you can never see S2P2, for example. Why? Because S has 1 orbital. It cannot be S2P2. That doesn't exist. You cannot, for example, see sp4. Why? Because p has 3 orbitals. No way you're going to have sp4. Okay, so that has an sp3 hybridization. Let's go to the... If I have AX5 as a model, as a Vesper model, and again for the electron pair geometry, I'm going to have 4, 1 for S, 3 for P, that's 4, and 1 from D, that's sp3D. For AX5, definitely you need to know this table. You'll not be given this table in the exam. An example of that is PF5. I think this is the Lewis structure, definitely with the lone pairs on the F's. I'm not going to put the lone pairs in here, just for the sake of time. So it is AX5, so I know that the hybridization is sp3D1. So 1, 2, 3, 4, 5, it's add up to the 5. And the last example is AX6, which is SF6. So it is AX6, the hybridization is sp3D2. So 1, 2, 3, 4, 5, 6. So this is the hybridization in SF. Okay. Now we're going to do some eye clicking on this so that you can practice and see what I'm doing. I'm going to stop it at 1. Okay. So I'm going to stop it right here and check what you think. And I have undetermined answer in here. So the first thing that you have to do is Lewis structure so that you can figure the Vesper, because you can't look at this and figure out the Vesper. We already agreed on that when we were talking about the Vesper model. So your first step is the Lewis structure, the Vesper model, then the electron pair geometry, then figuring out where it's coming from. Then from there, you're going to determine the hybridization. So again, Cl is a central atom, fluorines, 3 fluorines. The N total, I have 1, 2, 3, 4, all belongs to group 7. That's going to end me up with 28. I have 1, 2, 3 bonds, minus 6 electrons in bonding. So I'm left with 22 electrons. I'm going to put 6 electrons on each as lone pairs, so that's 18. So I'm left with 2 lone pairs on this. So mainly it is AX3E2, which is coming from AX5. That implies that the hybridization is S. I can't put S2 or S3. P, D, so 1, 2, 3, 4, 5. So the hybridization is sp3d, which is A. So A is the right answer. So if you jump through the steps, 50-50, you're going to get it right wrong. If you just decide, oh, it's AX3, definitely you're going to get it wrong. So definitely you need to write the Lewis structure, Vesper model, then the electron geometry model of Vesper, then you decide the hybridization. Let's do some more. This is a little bit different question. How many sigma and pi bonds are there in C2H2?
Wait, it's
I'm gonna stop it at 140. Okay. So I'm gonna stop it right here and check what. And I have B to be 76%. Great job. B is the right answer. So what you should do first, Lewis structure. So mainly it's carbon. Hydrogen can never be the central atom, so I'm going to connect the carbon to the carbon. Whenever I'm dealing with hydrocarbons, which is carbon and hydrogen, I do it in a symmetrical way. So I'm going to put one hydrogen to this, one hydrogen to that, then N total equal 2 times 4 plus 2, 2 hydrogens equal 10 electrons. 1, 2, 3, 6 electrons in bonding. That ends me up with 4 electrons. I can't put lone pairs on hydrogen, they only need 2 electrons. So I'm going to put it this way and this one, or on the other one. Then I'm going to see that this carbon needs electrons, so I'm going to borrow, and I'm going to end up with this Lewis structure. I know that every single bond is a sigma bond. This is a sigma, this is a sigma, and pi and pi. The double and triple bonds are pi, so 3 sigma, 2 pi's, which make B the right answer. Let's do some more of that. How many sigma and pi bonds are there in ammonia and H3? Okay, so I'm going to stop it right here to check what you think. Okay, great job. D is the right answer. So again, I'm going to Lewis structure. This is the Lewis structure. I have 1, 2, 3 single bonds. Single bonds are sigma bonds, so 3 sigma bonds. Okay, what about C2H4? Okay, so I'm going to stop it right here and check what you think, guys. Very good. D is the right answer. Again, this is carbon connected to carbon. Hydrogen cannot be central atoms. I'm going to do it symmetrical because it's a hydrocarbon. So I'm going to put 2 H's here, 2 H's there. And total is 2 times 4 plus 4. That's a total of 12 electrons. I have 5 bonds minus 10 electrons. I'm left with 2 electrons. I'm going to put it in here. Then I'm going to share it. So this is a sigma because it's a single bond, sigma, 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 sigma. The double bond, the second bond is a pi bond. So it is 5 sigma and 1 pi. Okay, I think we still have 2 more to go. What about this one? What is the hybridization of carbon A and oxygen B in the following molecule respectively? And I'm going to stop it at 1. So stop it right here and check what you think comes. 65%. That's good. C is the right answer. So let's start with A, the carbon. It is the vector model is AX3. Therefore, it's an sp2, 1, 2, 3. It adds up to that. And the oxygen is AX2E2. That's the electron pair geometry gonna be AX4. That's an sp3, 1, 2, 3, 4. It adds up to that, which makes C the right answer. That we've done from the first part of iClickers about valence bond theory. Now, we still have one. Sorry, but let's do that. What is the hybridization of the carbon in CO2 and how many sigma and pi bonds are there? I'm going to stop it at 1 minute. Okay, so I'm going to stop it right here and check what you think of. And I have C to be 97%. So let me see. So CO, CO. And I have AX2, that means SP, that's 5. And I have 2 sigma, 2 pi, and which makes C the right answer. Okay? I'm going to stop right here and have a wonderful weekend. I'll see you Monday.